Hello everyone. So in the previous video we all learned about the radial wave function. In this video we will learn about the angular wave function and especially the shape of the atomic orbitals. Okay. So at first I will just do little bit recapitulation of the previous videos. Then I will start the today's topic. Okay. So let's start the today's video. Okay. So in the previous videos we learned that related to every atomic orbital, in the previous video we all have learned that in the related to every atomic orbital there is a mathematical equation, and that mathematical equation is called wave function, and that is basically denoted by a letter psi, and that equals to radial wave function into angular wave function, and this depends on three quantum number n, l and m, that means principal quantum number, azimuthal quantum number and magnetic quantum number. This radial wave function depends on principal quantum number and azimuthal quantum number, and this angular wave function depends on azimuthal quantum number and magnetic quantum number. Okay, we all have learned this thing. Okay, now in the previous video we have discussed about the radial wave function and what is the probability density and what is the relation between what is the graphical relation between r of r and the distance. Okay, in the previous video we already have learned these kinds of things. Okay, so in this video we will basically mainly we will talk about the angular wave function. Okay, now in the video of in the video of node and nodal planes, we discussed that if y, l and mod of l, that means angular wave function phi equals to 0 at any point in the three-dimensional region. Okay, in the three-dimensional region, if at any region the angular wave function equals to 0, that is called angular node. That is called angular node, and number of angular node equals to the azimuthal quantum number L. Okay, now today we will discuss about the functional forms of angular wave function for various types of orbitals and try to figure out the shape of the atomic orbitals. Okay, but most important thing in this topic is that you have to know about the radial plots. Okay, you have to know about the polar graphs. Okay, how to draw a polar graph. So you all know that the reference systems can be made by two ways. One is called Cartesian coordinate system, and another one is called polar coordinate system. Okay, so in today's lecture we will mainly discuss about the polar coordinate system. Okay, and this is very much applicable in the concept of physics and chemistry. Okay, so that's why before the discussion of angular wave function we will little bit see about the angular polar graphs. Okay, and polar coordinate system. Okay, now let's say this is my reference axis. Okay, and let's say there is a point. Okay, this point in this plane, and I want to specify the position of the plane. Okay, position of the point. So what I can do, I will draw a line from the origin. And let's say this distance is r, and this distance makes an angle with this reference line theta. Okay, so according to the polar Cartesian coordinate, I will write the position of this point r comma theta. Okay, so according to the polar Cartesian coordinate, according to the polar reference system, okay, I will tell that the position of the point equals to r comma theta. Okay, let's at first understand the example. Okay, if I give you a point 2 meter comma 30 degree, so how I will represent this point in the polar graph? At first, take 2 meter distance from the origin. So I am trying to I am trying to represent this point 2 meter comma 30 degree in polar graphs. Okay, so what I will do, at first I will draw a 2 meter distance along this reference line. So let's say this is my 2 meter distance. Okay, now then this makes an angle 30 degree. So then I will rotate this 2 meter at the 30 degree angle, and I am reaching this point. Okay, so that means this is my 30 degree. So this is 2 meter and this is my 30 degree. So this point represent 2 comma 30 degree angle. Okay, so this is called polar graphs. Okay, so that means at first draw a distance along the reference axis, then rotate the rotate the line on specific angle that is present on the coordinate system. Okay, so this is a little bit about the polar graphs. Okay, and this information is sufficient. So this little bit information is sufficient for us. Okay, now let's go for the angular wave function. Okay, so in angular wave function, okay, so in case of angular wave function, we will at first look at the angular wave function of 1s orbital. Okay, so 1s orbital. Okay, so for the 1s orbital, my quantum numbers are, for the 1s orbital, or n equals to 0, L equals to 0, and M equals to 0. Okay, so what should be my quantum number? What should be the representation of angular wave function? So I will write it theta phi 0 0. Okay, so as this is mainly represents the 1s orbital, I will simply write it angular wave function of 1s orbital. This represents angular wave function of 1. And according to the calculation of Schrodinger, this wave function equals to 1 upon 4 pi to the power half. Okay, 1 upon 4 pi to the power half. So that means the angular wave function of 1s orbital does not depends on theta and phi. Okay, so that means the angular wave function of 1s orbital does not depends on theta and phi. Now if I want to draw a polar graph. Okay, now if I want to draw a polar graph, okay, so let's say this is my reference reference line. Okay, so if I tell that what is the, I am writing theta, okay, and I am writing the value of 1s. Okay, so if I tell at the 0 degree angle, okay, what is the value of angular wave function for 1s orbital? This is 1 over pi to the power half. If I tell at the 30 degree, what should be the value? This is again 1 over pi to the power half. If I tell what is the value at the 45 degree, or if I say directly 90 degree, the value will be 1 over the power half. Okay, if I say what is the value at you can say what is the value at 180 degree, so you will find that to the power half. What will be value for 270 degree? So this is also again 4 pi to the power half. And what will be the value at 360 degree? You will simply tell that 1 by 4 pi to the power half. Okay, so that means that means it simply shows that because as there is no theta term in this equation and this 1 by 4 pi is a constant, so that means for 1s orbital the angular wave function is a constant. Okay, so the angular wave function is a constant. So that's why this does not depend upon the angle theta, okay, or angle phi. Okay, so if I want to plot, so at the 0 degree angle, so that means my reference line will be along this line. Okay, so at the 0 degree angle the values of 1 by 4 pi, the values of angular wave function is 1 by 4 pi to the power half. If I say that this distance represent the value, this distance represent the value 1 by 4 pi to the power half. This distance represents the value 1 by 4 pi to the power half. So that means I am telling this distance. Okay, so this is 1 upon 4 pi to the power half. Okay, now at the 30 degree angle. Okay, so at the 30 degree angle the value is same. At the 30 degree angle the value is same, the 1 by 4 pi to the power half. At the 90 degree angle the value is same. Okay, at the 180 degree the value is same, and at the 270 degree the value is same, and at the 360 degree again the value is same. So if I just join all the points, if I join all the points, so this point is 0 comma 1 by 4 pi to the power half. Okay, so this point is this is wrong representation. I have to at first I have to specify the distance. Okay, so at this is 1 by 4 pi to the power half comma 0 degree. Okay, then again 1 by 4 pi to the power half, this is 30 degree, this is 30 degree, and this point, okay, this point is 1 by 4 pi to the power half 90 degree, this point 1 by 4 pi to the power half comma 180 degree. Okay, and this point is 1 by 4 pi to the power half comma 270 degree. Okay, so this is the coordinates of the points in the polar coordinate system, and when I am joining all the points, I am getting a circle in the two-dimensional sphere, in the two-dimensional graph. Okay, now if I draw a three-dimensional graph, so if I simply rotate a circle in three-dimensional axis, if I just simply rotate a three-dimensional axis, what I should get? I should get a sphere. Okay, so this is a this is a circle in two-dimensional figure. So what is the corresponding figure in what is the corresponding figure of a circle in three dimension? So in a three-dimensional space, the corresponding figure of a circle is sphere. Okay, so that's why if I rotate the circle in three-dimensional space, I will get a sphere. Okay, so that's why we tell that the shape of the s orbital is spherical. So that's why we always tell that the shape of the s orbital is spherical, because the angular part of the s orbital is constant, and the value of constant is 1 by 4 pi to the power half. Okay, so that's why always, so in our entire chemistry, when we are talking about the s orbitals, so that's why we always write the s orbitals by a circle or sphere. Okay, so that's why we always represent a 1s orbital by a sphere. The logic behind this the logic behind drawing this 1s orbital by a sphere is that the angular part of this wave function is constant, and the value is 1 by 4 pi to the power half. So that's why always we are trying to draw the 1s orbital, or try to represent the 1s orbital by a circle, and tells that the 1s orbital is spherical. Okay, spherical. So it's spherical shape. Okay, now, so number of radial nodes. So we are getting that for 1s orbital the values of L equals to 0 and the number of number of angular nodes equals to the azimuthal quantum number. So that's why the azimuthal quantum number is 0. So number of angular node for 1s orbital equals to 0. So that means here no angular node is present. Okay. Now let's go for the p orbitals. Okay. Let's go for the p orbitals. So if I simply said, let's say 2p orbital. Okay. So here n equals to 2, my L equals to 1. Okay. My L equals to 1. Now how many m values are possible? So this is simply 1, 0, minus 1. Okay. 1, 0, minus 1 because the values of m contains minus L to plus L. Okay. Including 0. So 1, 0, minus 1. Okay. So that means here if I want to write the angular wave function, I can write y. So this is L here, the values of L equals to 1, but corresponding to 1 there is a 3 value. So I can write 3 angular wave function. So here is an important point that corresponding to every corresponding to L equals to 1 there is a 3m value. Okay. Now the general representation of angular wave function is L mod of m, theta and phi. So that means the values of y equals to 1, but there is a 3m values. So I can write y equals to 1 theta phi, y 1 0, this is theta and phi, and y 1 minus 1 theta and phi. So that means in case of p orbital I am getting 3 angular wave functions. The most important the most observable point in this part is that for the p orbital I am getting 3 angular wave functions. Okay. So that's why we are getting, for due to these 3 angular wave functions I am getting 3 p orbitals. Okay. So due to this 3 angular wave function I am getting 3 p orbitals. Among these 3, one is called okay, I will write in this direction. Okay. And these 3 are classified, these 3, so I am 3 angular wave function. One is called px, one is called py, and another one is called pz. Okay. So that means I am getting 3 angular wave functions. So that's why we tell that p orbitals has 3 orientations. Okay, one is called px, one is called py, and another one is called pz. Now we will try to find what is the shape of p orbital and what is the meaning of px and py and pz by this angular wave function. Okay. Okay. So at first I will start with pz orbital. Okay. Pz orbital. Okay. So the angular wave function for pz orbital equals to a constant into cos theta. Okay. A constant into cos theta. Okay. A constant. So the wave function for angular wave function for pz orbital, angular wave function for pz orbitals equals to angular wave function for pz orbital equals to a cos theta. Okay. So now I will try to draw a graph of this, polar graph of this angular wave function. Okay. So let's start. Okay. So at first I will try to make a data table, and for the simplicity what I will take that a equals to 1. Okay. I will take a equals to 1. This is the values of a equals to not 1. Okay. But if I want to draw the polar graph taking the values of real values of a, so this is very much complicated. Okay. So for the simplicity I will take that a equals to 1. So what will be my wave function for pz equals to cos theta? Simply the cos theta. Okay. Now how will be the graph. Okay, so at first I want to make a data table. Okay, so let's say this is my value of cos theta, and in the below I am presenting theta. Okay, now I want to write some data. Okay, so if I take theta equals to 0, what should be the value of cos theta? So the values of cos theta will be 1. Okay, now if I tell the values of theta equals to 30 degree. Okay, so what should be the value? Fractional value is 0.85. Okay, now if I tell the value is angle is 45 degree, so what should be the value? Value should be 0.7071. Okay, now if I tell the angle is 90 degree, sorry, if I tell the angle is instead of 90 degree, there's an in between very much familiar angle, this is 60 degree. Okay, so if I tell angle is 60 degree, so my value will be 0.5. Okay, then if I tell this is 90 degree, if I tell this is 90 degree, so that means this is 0. Okay, if I tell this is 90 degree, so that means the value is 0. Okay, okay, now if I further increase the angle, if I say 120 degree, so the values of cos 1 to 120 degree is minus 0.5, minus 0.5. Okay, now the value of if I increase the angle with 135 degree, so the value is minus 0.707. And if I increase the angle with 1, let's say my angle is 150. Okay, if my angle is 150, the value is minus 0.8, just the reverse of these angles. Okay, and if my angle is 180 degree, so this is 0. Okay, if I say the angle is 180 degree, so my value will be 0. Okay, so I will write this in here. If theta equals to 180 degree, okay, so cos theta equals to, okay, let me write. Okay, so if theta equals to, okay, so if theta equals to 180 degree, the value equals to 0. Okay, again the value equals to 0. Okay, so if I start drawing the graph, so when the angle is 0, okay, when the angle is 0, okay, when the angle is 0, so when the angle is 0, so my plot is, so this is the 0 angle. Okay, let's say I am drawing a line along this reference line, and this distance is 1. Okay, unity, this distance is unity, so this line, so this is 1 and the angle is 0. Okay, so this is the point 1 comma 0. Okay, now the next point for this is 30 degree. Okay, so in case of 30 degree, so in the polar graph at previously I am considering the angle from the x axis, but now I am considering the angle with y axis. Okay, because this makes my graph little bit clear, okay, and easier. Okay, so for the 30 degree angle, let's say this is the 30 degree angle, this is the 30 degree angle, and my value is less than 1, so 0.15, so that means less than, let's say this is, so this is my point, so this point is 0.85 comma 30 degree. Okay, now, okay, I will not write the points here because okay, I will draw the graph with bigger in size. Okay, so let's say this is my axis and I am taking the angle from 0 degree. Okay, so let's say uh, this is my distance 1. Okay, let's say this distance is 1 unit. Okay, so I am taking the angle with y axis, so this is 1, so this point is 1 comma 0 degree. Okay, now if I take 30 degree, so at first I will make an angle 30 degree, then at the 30 degree my distance is, the value of cos theta is 0.85, so this point is 0.85 comma 30 degree. Okay, now then for the 45 degree angle, okay, so this is 0.7, so less than that. Okay, I'll not take this line as 45 degree because I have to also draw a line for 60 degree, so that's why I will make the line little bit closer. So this is, if this distance is 0.85, so that means this, for the 45 degree angle, let's say the value is 0.7. Okay, so that means if I take this distance, okay, so this is 0.7 comma 45 degree, and if I draw a line for 60 degree, so what is the value? This is 0.5. Okay, so 0.5 comma 60 degree, and for the 90 degree, so this is the 90 degree distance and the value is 0, so that means the point is here. Okay, now if I continue the drawing the graph, so if I take 120 degree, okay, so let's say this is a point which is 120 degree basically. Let's say this is the 120 degree point, so the value is 0.5, so let's say this is minus 0.5, so minus 0.5 comma 120 degree, then my value is 135, my angle is 135 and my value is 0.7. Okay, so 0.7 comma 135 degree, then my angle is 150 degree. Okay, 150 degree, sorry, for the 180 degree value. Okay, so this will be, let's say the value is 0.8, so 0.8 comma 150 degree, and last value is 180 degree, so this is 180 degree direction, and the value is, sorry, this is minus 1, cos 180 degree equals to minus 1, so this is, if this is 1, so this direction is minus 1, so this point, so this is minus 1, 180, so this is minus 0.7 minus 0.8. Okay, 180 degree. Okay, so if I just draw these things, these points, if I draw these points, what I am getting basically, so I am getting this kind of a shape. Okay, I will draw the points little bit clear, it looks better. Okay, so if I just join the lines, so now if I continue the drawing, if I continue to draw the graph in this section, I will also find this kinds of a part, and if I try to draw the graph in this direction, I will also try to find this kinds of a graph. Okay, so this angle is 30 degree, this angle is total, this angle is basically 45 degree, and this angle is 60 degree, and the total angle is 120, then 135, then 150, 180. Okay, so I am basically drawing a polar graph. I am basically drawing a polar graph. Okay, I am basically drawing a polar graph of cos theta versus theta. Okay, so in this direction along the line my coordinates are, so basically my, if I write the general coordinates equals to y of pz comma theta. Okay, y of pz comma theta, and if I plot the radial polar graph of the pz angular wave function of pz orbital, I am getting this kinds of a shape. Okay, so this is the this is the general shape of the orbital. Okay, so that's why always we are trying to write the p orbital in this fashion. Okay, so that's why in always we are always try to draw the z orbitals in this fashion, p orbitals in this fashion. Now if I simply rotate this p orbital, this is a two-dimensional figure. If I simply uh, try to rotate this figure around this axis, so what happens? I will get a three-dimensional figure which is dumbbell shaped. Okay, so that means if I rotate this figure around the if I just draw this kinds of graph in a three-dimensional figure, so what I should get? I should get a dumbbell like shape. Okay, so that means why p orbitals are written in this fashion, because the wave function of pz, if I draw the radial wave function, if I draw the polar graph of a polar graph of the angular wave functions, I will get these kinds of a shape. Okay, so what the basic concept is coming out, that the p orbitals, the shape of the p orbital means it's nothing but the graphical presentation of the angular wave function. Okay, this is nothing but the shape of the orbitals, dumbbell shaped or spherical shaped, this is nothing but the graphical presentation of the angular wave function. Okay, this is a graphical presentation of the angular wave function. Okay, in polar coordinate system. Okay, now I think it's clear. Okay, so we are just we are in this section we are just trying to draw the polar graph of cos theta. Okay, so this is the result. Okay, now what happens? Why this orbitals are called px p? Now why this is called pz? Okay, so pz means, why this is called pz? Okay, so pz means, in the very beginning lecture we see that we're assuming that this is x axis, this is y axis, this is z axis, and nucleus is present at the origin, and let's say electron is present at the distance r. So if this angle is theta, so along the z axis, so z equals to, we have written that in the previous lectures, we have written that z equals to r cos theta. Okay, now what is the value of y? This is r sine theta. Okay, so this value is r sine theta. Okay, now if this angle is phi, so y equals to sine theta sine phi, and x equals to r sine theta cos phi. Okay, cos phi. Okay, now from this equation, if we does not require these two equations. Okay, we does not require these two equations. If I simply write this, okay, so distance from the nucleus to electron is r, and this angle is theta, so that is z equals to r cos theta. Okay, now here the term is present a cos theta, so cos theta equals to here z by r, so I can write y of pz equals to a z by r. Okay, so that means angular wave function depends on the z part, so that's why this angular wave function, so that's why we can tell that angular wave function depends on the z value of the Cartesian coordinate system. So angular wave function depends on the z value of the Cartesian coordinate system. So that's why this p orbital is written as pz orbital. Okay. Now the value of azimuthal quantum number is 1, and we all know that the angular node equals to the azimuthal quantum number L. Okay, number of angular nodes equals to the azimuthal quantum number L. Okay, so that means pz orbital should have one angular node. Okay, so if I just simply, if you want to know the angular node, angular region of angular node of pz orbital, so simply what you have to do, this z, just put z equals to 0. Okay, so what is the meaning of z equals to 0? Okay, so the meaning of z equals to 0 is, let's say, okay, let's say this is x, this is y, and this is z. Okay, now in this xy plane, okay, in this xy plane, if you just look carefully, in this xy plane, this is the xy plane. Okay, so this is the xy plane, and in this xy plane, the all the points that present on this xy plane, the values of z equals to 0. All the points that is present on the xy plane, the values of z equals to 0. So that means if I put z equals to 0, that means this represents the xy plane. Okay, so xy plane. So that's why this xy plane is the nodal plane of the pz orbital. So that's why this xy plane is the nodal plane of pz orbital. Okay, nodal plane of pz orbital. Okay, now let's try to represent the pz orbital. Okay, so so let's say this is my y-axis, this is my x-axis, and this is my z-axis. Okay, so this is my x dash, y dash, z dash. Okay, so the pz orbital should looks like that. Okay, okay, so my pz orbital should looks like that. So this is the shape of pz orbital, and this plane, this is the xy nodal plane. Okay, so simple way to remember that, the z, so z, if I put z equals to 0, so this represents my xy plane, so that means the xy plane is the nodal plane. Okay, so this is the nodal plane of pz orbital. Okay, and that is the represent. Now look at this phase, so this phase, the upper part of the pz orbital present in the positive the positive value, this positive axis of z. Okay, so this upper part present along the positive z axis, so that's why this upper part is called, denoted by positive, and the lower lobe, the upper lobe of this p orbital, the upper lobe of the pz orbital is present by plus sign, and the lower part, as the lower part is present in the negative part, lower part is present in the negative part of the z axis, so that's why this is represented by minus, and this plus minus are called the phase of the orbitals. Okay, these are the called phase of orbital, phase of orbital. Okay, now, and this is called dumbbell shape. Sorry, this is not the correct spelling for dumbbell. Dumbbell shaped. Okay, so this is the all about pz orbital. So I think it's clear to everyone that why this is called pz orbital, because in the angular wave function, this wave function only depends on the z value, okay, z value of the Cartesian coordinate. So that's why this is called pz orbital, and the angular wave function contains a cos theta part. And if I plot a if I draw a radial polar graph of cos theta function, so I will get this kinds of shape. So that's why pz is written in this fashion. So that means the dumbbell shape is nothing but the graphical presentation of the angular wave function. Okay, so this is nothing but the graphical presentation of angular wave function. Okay, okay, let's go for the other p orbitals. Okay, so then go for py. Okay, now in case of py and px, so the wave function y py equals to a constant into y upon r, and for the x, px equals to a into y upon, sorry, I will write this in small, x upon r. Okay, so as this wave function contain the y part in the angular wave function, so that's why this is called py, and the meaning of px equals to this angular wave function only depends on the px. Okay, and in case of pz, this is y pz equals to a into, a is a constant, okay, z upon r. So when the wave function depends on z, the lobes are present along the z axis. So from the generalization I can tell that for the py orbital, as this angular wave function depends on y, then the lobe should be along the y axis. Okay, so that means if I just try to draw the graph. Okay, so now what should be my nodal plane? So if I put y equals to 0, so this represent xz plane, and that is nodal plane. Okay, so this is my y direction, this is my y direction, this is my z direction, and this is my x direction. Okay, so this is x dash, y dash, and this is z dash. Okay, now so this py depend, the angular wave function of py orbital depends on the values, only the values of y. So that means the lobe should be present along the y axis. Okay, now as this part is present along the as this part, so I think if I just clear this part, it should be little bit more clear. Okay, let's say this is my orbital. Okay, okay, let's say this is my orbital, and as this part lobe is present along the positive y direction, so this is positive, and as this is present at the negative y direction, so that means this is negative. So, and this is the phase of the orbital, and this is the xz plane node, and this is the nodal plane. Okay, this is the nodal plane. Okay, so this is the nodal plane, and this is the shape of py orbital. And in this graph, if I want to draw the px, only for the px orbital, the wave function only depend on x, so that's why I can write the lobes like that. Okay, this is my px orbital. Okay, this is px orbital. Okay, so this is px orbital. Okay, now let's summarize. So for P, there is a three type of orbital, PZ, PY and PX. Okay, all are dumbbell shaped. Okay, shaped with one nodal plane. Okay, now so okay, so for PZ, if I put Z equals to 0, so what it represents? It represents XY. Okay, so I am writing this plot as nodal plane. Okay, so for the PZ, if I put Z equals to 0, so I will get, so XY plane. Okay, so for the PZ orbital, nodal plane is XY plane. If I put Y equals to 0, that means XZ plane. XZ plane is the nodal plane, and for the XY, definitely YZ plane is the nodal plane. Okay, YZ plane is the nodal plane. Now, why this is called nodal plane? Okay, so if you just simply look at the situation, this is plus and this is minus, and all the nodal planes are present along this. Okay, along this plane. Okay, and when you are passing from this to this, you are basically your the phase of the orbital changes from plus to minus. Okay, so that's why in this region you cannot find the electron density. So that's why this region is called nodal plane. Okay, you cannot find electron density along this plane. Okay, now there is also a definite meaning of these shapes. Okay, so if I tell that the shape of the orbital is like that, so that means in the three-dimensional region, if I draw the axis, okay, in the three-dimensional region, within this region, the probability of finding of electron around the nucleus is maximum. So that means the shape of the orbital means, so within this region, within this two region, probability of finding a electron is maximum. So that's why we are drawing these regions by these kinds of special shape. Okay, so that means within this regions, and this within these two regions, you can, the probability of finding electron, specifically the electron which is present in 2p, is maximum. Okay, so that's why this is called orbital. Okay, so that's why sometimes the definition of orbital is written in such a manner that uh, orbital is a three-dimensional space around the nucleus where the probability of finding electron is maximum. Okay, so sometimes in the books the definition of orbitals written in this manner. Okay, okay, now let's go for the d orbitals. Okay, so let's say d orbital. Okay, so the value of L equals to 2, so possible value of m equals to -2, -1, 0, +1, +2. So if I want to write the spherical harmonics, angular wave function, so -2 y 2 -1 y 2 0 y 2 +1 y 2 +2. So five possible angular wave functions. Okay, five angular functions are possible for the d orbital. Okay, so five angular wave functions are possible for the d orbital. So that's why in case of p orbital, we always say that in case of in case of d orbitals, we tells that there is 5 type of d orbitals. Okay, so at first writes the traditional name of the 5 type of the d orbitals. Okay, so these orbitals are simply called d orbitals are 5 types. Okay, one is called dxy, dyz, dxz, dz square, dx square minus y square. Okay, Now one by one I will tell why this is called dxy, this is why this is called dyz, why this is called xz. Okay. So in case of d, at first start with dxy. Okay. At first start with dxy. Okay. So in case of dxy, okay, dxy, why we call this is as dxy? Because if I write the wave function for dxy, angular wave function, a constant xy upon r. Okay, so that means that as the wave function depends on x, the values of x and y, so that's why this wave function is written as x into y. Okay, now look at the values of L. This is L equals to 2. That means the number of angular node for this d orbital equals to 2. Okay, so again I will apply the same strategy to determine the nodal planes. Okay, so just put xy equals to 0. Okay, xy equals to 0. So that means x may be 0 and y may be 0, and if x may be 0, this represent yz plane, and if y equals to 0, this represents xz plane. So that means these two planes are the nodal planes. Nodal planes for xy plane. Okay, these two are the nodal planes for the xy orbital. Okay, dxy orbital. Now let's look at the shape of so let's say this is my y-axis, this is my x-axis. Okay, my x-axis is not, this is not correct. So let's say this is my x-axis, x dash, y dash. So that means this plane is a xy plane. Okay, okay, so this is my coordinate system, z dash. Okay, so xy, the dxy looks like that. Okay, and if this is positive phase, this should be positive phase, so that the opposite lobes are in same sign for the dz orbital. Okay, in case of p orbital the opposite lobes are negative. Okay, because this is the nodal plane. Okay, but in case of d orbitals, the opposite lobes are not nodal planes. So opposite lobes are in same phase. Okay, if this is positive, this is also positive. If this is negative, this is also negative. If you write this is negative, you have to write this is also negative. If you write this is positive, you have to write this is positive. Okay, now look at this shape. Okay, so this orbital is basically present on the xy plane. Okay, so this is basically present on xy plane. This is present on the xy plane. Okay, and what is the nodal plane? This is yz. Okay, so yz means, so my drawing is little bit wrong because this is touches the yz axis. This is not the correct way, so I should draw this like that. This is minus. Okay, and this is my z axis. Okay, so this is my z axis. Okay, so this is my z axis. Okay, so look at the picture. So this plane basically, so there is a two nodal planes. Okay, one nodal plane is yz. So this is y and this is z. So that means this plane is a nodal plane, because if you cross the line here, you are going from here to here, you are getting plus to minus. You are going here to here, you are going plus to minus. So this is a nodal plane. and another nodal plane is xz. Xz means this is x, this is z. So that means this plane, that means basically the plane made by these two axes is a nodal plane. Okay, so this one, so if you cross this line, you are also getting the same thing, plus to minus, plus to minus, minus to plus, plus to minus. So as, so that means simple concept, if you cross a nodal plane, your sign of the phase of the orbital should be changed. So along these lines the orbital phase is changed, so that's why these two are the nodal planes. Okay, but how you will find the nodal planes? Just put the values of xy equals to 0. So xy equals to 0, xy equals to 0 maybe happen due to the x equals to 0. So this, and x equals to 0 means yz plane, y equals to 0, that means xz plane. Okay, as y equals to 0, that means the values are remaining for x and z. So that's why this is the presentation of xz plane. They are the planes. Okay, plane, okay, planes. Okay, so this is all about the dxy orbital. Okay, now if I simply want to yz orbital, dyz orbital. Okay, so how will find the nodal planes? Yz equals to 0, so it may be happen due to y equals to 0, or it may be happen due to x equals to 0. Y equals to 0 means, y equals to 0 means xy plane, and y equals to 0 means x, sorry, z equals to 0, sorry, y equals to 0 means xz plane, and z equals to 0 means xy plane, and these two planes are nodal planes. Okay, so these two are the nodal planes. Okay, so what is the shape of the orbital? If I draw the axis, okay, so this is my y dash, x dash, z dash. Okay, so the orbital looks like that. Again, like the previous case, if this is plus, this is also plus, if this is minus, this is also minus. Okay, so this is the shape of the orbitals. And look at the case xz plane. Okay, so this is x and this is z. Okay, so this orbital, sorry, this is I am drawing the xz orbital. Okay, because this orbital is present on xz plane, so this plane is xz plane. Okay, on this plane we are finding this four lobe, so that's why this is xz plane. So this should be not my not my nodal planes. So nodal plane should be xz, so that means it can be happened by two way, x equals to 0 and z equals to 0. So that means this is yz and this is xy. Okay, so these are the nodal planes. Okay. So yz means which one plane? This is y and this is z, so that means this line is the nodal, this plane is the nodal plane. Okay, and another plane is xy. Okay, xy means the plane of the boat. Okay, these two are the nodal planes. Okay, actually it's very much it's little bit difficult to show the nodal planes in this picture. Okay, now let's go for the same way. You can draw the nodal planes for xy orbital. Okay, and shape of the xy orbital is same. Okay, if I draw xz, sorry, okay, xz, so if I draw xz, so let's say this is z orbital, z axis, this is y axis, this is y axis, okay, and this is my x axis. If I draw xz orbital, if I draw basically yz, if I draw yz orbital, so this yz orbital basically looks like that, okay, and this is present on the plane of board, okay, and this is d yz, okay, this is dy z. So yz means the the orbital is present on the yz plane, okay, and the node, how you will find the node, you will find the node y equals to 0 and xy equals to 0, and xy equals to 0 can be happened by two ways, and this is represents y equals to 0, so that means this is xz plane, and y equals to 0 xy plane. So these are the nodal planes, okay. Okay, now the most important part is for d x square minus y square, okay. So for the d x square minus y square, so I will find the node. So x square minus y square equals to 0, x square minus y square equals to 0, so x square equals to y square, so x equals to plus minus y. So that means from here I am getting two equations, x equals to y, x equals to minus y, okay. So now if I draw a axis, okay, if I draw axis, so let's say this is x axis and this is y axis, okay, this is x axis and this is y axis, okay. So okay, at first, okay, let's draw the 3D picture, okay, let's draw the 3D picture. So this is my z axis, this is my y axis, this is my x axis, okay. So x equals to y, so that means this represents this straight line, okay, this represents this straight line, okay. So this is x equals to y, and x equals to minus y, so that means this is represent this or line, x equals to minus, sorry, I will write it clearly, x equals to minus y. So that means now xy or dx square minus y square cannot present along these lines because these are the nodal planes, okay. So that means the next possibilities, it can present along the planes, okay. So this is the orbital, okay, this is the, so if I write this is plus, this should be plus, if this is minus, so this should be minus, okay. So this is the dx square minus y square. So most important observable point is here that the lobes, all the lobes are present along the axis, okay. This is along the x axis and this is along the y axis, okay. So in case of dxy orbital, this dxy orbital is also present on xy, this is xy plane, okay, because this plane is made by x axis and y axis, so that's why this is xy plane, okay. So in case of dxy, this plane the dxy is also present on xy plane, but and dx square minus y square is also present on the xy plane. What is the difference? The difference is that the dxy is interaxial orbitals, and dx square minus, in case of dx square y square, the lobes are present along the along the axis, and in case of dxy, these lobes are present along the in the intermediate distance of two axes. So that means the dxy is interaxial orbitals, and dx square minus y square is the lobes of dx square minus y square is along the axis. Okay. So now let's come to dz square. Okay. Now important point for dz square is that if I draw, let's say this is z axis. Okay. Let's say this is z axis. If I draw the z square, so in case of if this is plus, this also plus, and minus and minus. Okay. Now let me allow to draw the all axis. Okay. So this is x dash, y dash, z dash. Okay. Now, so this is the shape of dz square. Okay. Now I want to write another picture of dz square. Okay. So in case of dz square, there is two little bit small lobes, and other two lobes are very much big. Okay. And they are in the same phase. Okay. So for dz square, I want to write another simple picture for the presentation of the nodal planes. Okay. Plus, plus, minus, minus. Now in the previous case we told that when I will cross a nodal plane, my sign should be changed. Okay. So in case of this situation, when I am passing from here to here, my sign change from plus to minus. So here I should get a nodal plane, and in this direction if I just go from here to here, I am getting also the phase of the orbitals is changed. So that's why in this direction, okay, let me allow to draw the line correctly. Okay. So along this direction, there is also a change in sign. So this is one nodal plane, and when I am going from here to here, also phase of orbital is changing. So that means this is a nodal plane. When I am going from here to here, so this is also there is a change in the phase of the orbital. So that's why the one nodal plane is along this line. Okay. So there is another line along this plane. Okay. Now if I just draw a circle here, so I am basically in case of dz square, if I connect all the two nodal planes, I am getting a cone. Okay. So that's why here in case of dz square, this is not a planar nodal plane. Instead of that, I am getting a conical nodal plane. Okay. So that's why if in case of in any question, if you find that for which d orbital there is no nodal plane, okay, so that means, so the answer should be dz square. Okay. Because this is not a nodal plane, this is nodal surface. Okay. Why this is not plane? Because this conical shape is not a plane, this is not a flat plane. Okay. This is a surface. Okay. So that's why the traditional term used for this conical shape is nodal surface. Okay. So that's why for dz square there is a nodal surface. Okay. There is no nodal plane. Okay. Okay. Let's summarize all the things. Okay. For dz orbitals. Okay. Okay. So for I will write here nodal planes. Okay. So dxy, yz, dxz, dx square minus y square, dz square. Okay. So for the xy plane, x equals to 0, that means yz plane is the nodal plane, and y equals to 0, that means xz plane is the nodal plane. Okay. So as y equals to 0, x equals to 0 yz, and y equals to 0 xz. So y equals to 0. So if y equals to 0, so that means this is xz plane, and if z equals to 0, that means xy plane. And for the xz orbital, the x equals to 0, yz plane, and for the z equals to 0, I will get xy plane. Okay, but for this case I am getting x equals to y, x equals to minus y. So I am putting x square minus y square equals to 0. So that means x square equals to y square. So x equals to plus minus y. So I am getting these two nodal planes. Okay, this also the planes. Okay, but in case of dz square, there is a nodal surface. Okay, no nodal plane. Okay, important fact is no nodal plane. Okay, nodal plane. Here only nodal surface is present. Okay, nodal surface is present for dz square, but no nodal plane is present. Okay. Okay. So this is all about the quantum mechanical model of atom, and we have finished the Schrodinger equation, the concept of probability distribution of wave functions. We have completed the the radial wave function. We have completed the angular wave function and the shape of the orbital. If you like my videos, please like, share and subscribe. Thank you.